Hi everyone. My name's Alex Jenkins. I'm a postdoc at the University of Cambridge, and I'm very happy to be part of this Multiverse from Home online conference. And I'm going to be telling you about some work that my collaborators and I have been doing over the past few years to try to understand the physics of vacuum decay, which, as I'm going to come on to in this talk, is a process that could have a lot to say about multiverse scenarios in the early universe. This is also a process that we actually have very poor theoretical understanding of at the moment, as I'm going to try to convince you. And so we are looking at new approaches for understanding this using tabletop experiments in the laboratory. So the goal will be to use these experiments to hopefully say something new about these kinds of multiverse theories that we're going to be talking about this week. So this is work that's been done with this really wonderful group of collaborators, which is a kind of very interdisciplinary mix between early universe cosmologists, but also people who are experts in the theory and also the experiments of cold atoms, which are the kind of experimental platform for these tabletop tests that we want to carry out. And in particular, I wanted to flag, so Matt Johnson, a collaborator of mine, is also giving a talk at this conference. So if you're interested in these questions about vacuum decay, I'm sure Matt will have some very interesting things to say in his talk as well. So the plan for the talk is I'm going to start by telling you what vacuum decay is, probably familiar to lots of people, but just to get everyone on the same page. And I'll try to say why it's interesting for multiverse cosmology, but also for lots of other open questions in early universe cosmology. Then I'll come on to telling you a bit about how we can simulate this process in the laboratory, and in particular about the analog experiments that I'm helping to try to bring to fruition. And then towards the end, I'll talk a bit about the theoretical work that I've been doing along with that group of collaborators to try to pave the way for these experiments and be ready for when this data comes to be able to extract some cosmological insights from them. So to start with, the basic picture is we have a single scalar field that obeys this Klein-Gordon equation, which looks very simple, except that this potential here, U, could be arbitrarily complicated. So we should picture our field as evolving in some kind of complicated potential landscape. And so in particular, it's not crazy to imagine that at some point in the universe's evolution, your field can get stuck in what is a local minimum of the potential, but it's not a global minimum. So the global minimum is really what we would call the vacuum state of the theory, the true vacuum. But this local minimum, it looks quite a lot like a vacuum state. So if I explore just small deviations away from this part of the potential, it looks like I'm in, yeah, what we would call the vacuum state of the theory. But if I can explore large enough deviations, so some kind of non-perturbative process, I can actually get down to this global minimum. And so this whole question of vacuum decay is how do I escape from this false vacuum and get down to the true vacuum? Now, if you were to do this everywhere all at once throughout the universe, then or throughout the multiverse, then that would cost a lot of energy because you have this big potential barrier here. So what tends to happen is that some localized region will transition first, and this forms what we call a bubble. And so then the bubble will want to expand, but this will be competing with the rate of expansion of the surrounding false vacuum, which is still in this higher energy state. So it's potentially if this is the field that's driving inflation, then the false vacuum regions are still inflating as well. So you have this kind of competition between those two rates. So this is quite a simple picture to think about kind of schematically. There's this nice cartoon here that I stole from a review paper by Mark Hindmarsh and collaborators. But the actual quantitative details of this process are really, really tricky to figure out because it's non-perturbative, like I said. Quantum effects are crucially important. And it's an out of equilibrium process as well. So this is a very difficult problem. So just to show you some images to kind of flesh out what I was just saying, this is a simulation video for a real-time simulation that I'm going to tell you a bit more about the kind of numerical methods later in this talk. But I just want to show, you start with this blue false vacuum state, which is kind of fizzing with these quantum mechanical fluctuations. This eventually leads to the formation of bubbles. The bubbles expand and collide. You have some transient kind of very complicated dynamics. And then eventually this whole region has transitioned. So this is the kind of process that we're interested in studying. So why do we care about this? I've already given a bit of a spoiler in that this is kind of the key process that underlies a lot of these theories of eternal inflation and multiverse scenarios. And in particular, in these scenarios, our entire sort of observable universe is contained within one of these bubbles, but there could be other bubble universes. And in particular, there people have thought in the past about how you could try to probe this scenario by looking at collisions between the bubbles and the imprints that would leave on the cosmic microwave background. But so, that's clearly the kind of main focus of this conference, but I come from this more from the direction of gravitational wave cosmology. So I'm really interested in, if these types of bubble nucleation processes happened within our own observable universe at some time after inflation, turns out that this is a really efficient mechanism for generating strong gravitational wave signals from the early universe. And in particular, the European Space Agency mission LISA is going to be a really, really nice probe of these transitions if they happened at or around the electroweak scale. And this could also happen in the present day. So based on the best data that we have from colliders like the LHC, it looks like the standard model Higgs might be sitting in a false vacuum state. And so if we wait long enough, it potentially, it could transition to the true vacuum and kind of destroy all of us because all of the couplings in all the particles in the standard model will change. So hopefully that won't happen. And based on our best understanding, the timescale for that it would be incredibly long if this is indeed the case. But this is a kind of, if you like, an existential reason for trying to understand vacuum decay as well. So as I was saying before, it's a really difficult process to try to understand in quantitative detail. So there have been methods that have been developed since the work of Sidney Coleman and collaborators in the 1970s, which were looking at using these Euclidean or imaginary time methods to describe these bubble nucleation events. And these give us really important insights, and they've led to a whole vast literature that underpins a lot of these applications I was talking about, like multiverse, gravitational waves, Higgs decay, etc. But I want to try to convince you that this formalism leaves a lot of really important conceptual questions and practical questions unanswered. So in particular, what does bubble nucleation look like in real time? If I can imagine sitting back and watching the false vacuum boil, what would this actually look like? It's not obvious how to take these imaginary time solutions that you can find and interpret what they would look like in real time. And this is particularly important if your background universe is evolving dynamically in real time, because then some of the assumptions that go into deriving the imaginary time solutions break down. You can also have situations where the symmetries of these imaginary time solutions are broken, and then it becomes much, much harder to derive concrete results using this Euclidean formalism. And this, the simplest example I can think of is, what if there is more than one bubble? So typically you would derive the solution for a single bubble nucleation by assuming basically O4 symmetry, and so some kind of generalized form of spherical symmetry, but extended to the 4D spacetime. But if I have two bubbles, then that clearly breaks, even just in space, it breaks that spherical symmetry. And so it's hard to write down a Euclidean solution for that. So, I could ask, okay, if I have more than one bubble, will those bubbles tend to be correlated with each other? Will they want to cluster together? That's something which we don't really have an answer for based on this Euclidean formalism. But as you can imagine, it would have a really, really important bearing on questions like, would I expect to see collisions between bubbles in the CMB if we are living in one bubble that is part of the multiverse? So this is a really crucial question for these kinds of scenarios and trying to probe them observationally. And indeed, to give you a bit of a spoiler, so I'm taking this figure from a really nice paper that was led by Dalila Pirvu at the Perimeter Institute, collaborating with Matt as well, Matt Johnson. And they find, using this simulation approach that I'm going to tell you about, they find that bubbles do indeed seem to cluster together. So this is a really important new kind of qualitative result that was missing from the Euclidean picture. So all of this sort of motivates, we want to go beyond the existing approaches and find new ways forward, new ways of understanding vacuum decay. And so one of these I've already talked about a bit, which is these real-time lattice simulations, and I'm going to come back to those towards the end of the talk. But another one that I'm really excited about is using these tabletop experiments to simulate this process of vacuum decay. So you build a quantum system in your laboratory, which obeys the same dynamics, the same equations of motion as a field undergoing vacuum decay in the early universe. And then you just watch it evolve and you let nature do all of the hard work for you of solving, the full kind of quantum dynamics of this system. And you can then just take pictures of it and see what happens and look for bubbles. So that's the general approach. And I'm going to now unpack a bit, exactly how we can build an experiment that would do this. So the experiment is not, this isn't a pipe dream. This is something that is actually happening and we actually have made a lot of progress towards. I say we, my experimental colleagues have made a lot of progress towards building this experiment. You can see a picture of a bunch of us here. So this is being built at the Cavendish laboratory in Cambridge, within the group of Zoran Hadzababic. And these guys are experts in making these really, really beautiful cold atom experiments. And so the thing that we want to do is not some kind of completely crazy futuristic thing, is using well-established techniques and capabilities within this cold atom community and just applying it to a new problem. So just exploring a different experimental regime where the system behaves like an early universe field. And so we're expecting the first science data, hopefully within the next kind of few months to a year, depending on how things go. So before I dig into the details of this system and how it emulates vacuum decay, I think it's useful to take a step back and think, okay, if I want to be able to extract new insights into the early universe from such an experiment, what are the criteria that it has to meet in order for that analogy to be rigorous? I want something that is not just a kind of loose analogy where something looks a bit similar, but I really want a detailed quantitative analogy so that we can take away actual physics insights. So one thing that we clearly need is a state within our system, our cold atom experiment, which is metastable, not just unstable. So you need it to be able to persist for quite a long time and then eventually decay by forming bubbles, rather than just immediately decaying to the ground state. Another thing that I would really like is for the system to be homogeneous in one or more dimensions. And this is because, clearly the early universe to a first approximation is homogeneous, whereas this is not the case for most of these cold atom experiments. Usually you have just a kind of, cloud of atoms that has some structure to it. Whereas we really want to build this experiment such that this atomic system is as uniform as possible so that we could see bubbles forming kind of in any part of the system. Getting more quantitative, I want one of the degrees of freedom within this system to obey the same equations of motion as the relativistic scalar field theory that I want to simulate. And then a separate but related point is I would like not just the kind of classical equations of motion for this system, but also the quantum fluctuations in this system to match those of the early universe theory. So these two things together kind of hopefully, guarantee that my system will behave like this quantum field that I want to study. And then finally, something that would be really nice, especially if we want to apply this to these kind of multiverse theories, is I would like to see quantum, vacuum dominated decay rather than thermal decays. So thermal decays would still be super interesting for early universe scenarios like the kind of electroweak phase transitions I was talking about before. But we really think actually that we will be able to get into this quantum dominated decay regime with these experiments. So yeah, indeed, all of these requirements we think will be met by the experiment that is being built. Okay, so let's get to the details of it. So what is this system? It's a cloud of atoms. They're bosonic atoms. And that means that if you cool them down to low enough temperatures, by which we typically mean, a few nanokelvin or something, they condense, they form a Bose-Einstein condensate. So rather than thinking about individual kind of point-like atoms, it's better to think their wave functions are very delocalized and they all start to overlap. And so we have this description in terms of this kind of many-body wave function. This is described by this equation I've written down here called the nonlinear Schrodinger equation. So it's very similar to, just the vanilla Schrodinger equation you would write down for a single atom's wave function. Except I have this extra nonlinear term, which goes like mod psi squared, which you can think of, well, mod psi squared is just the number density of of atoms within this many-body system. And so this extra term is just telling you about how each atom feels the presence of the other n-1 atoms by scattering off of them. And it turns out that this term is actually really, really crucial to get the kind of pseudo relativistic behavior that we want. So that's not very obvious that effective behavior drops out from this equation, because just staring at this, you might think, okay, well, if I want something relativistic, the kinetic term looks completely wrong, for example, and I don't see any potential with a false vacuum in it. So I'm going to try and flesh out over the next couple of slides how we can get this. So the first hint that you get something that looks relativistic comes from looking at the dispersion relationship for little fluctuations in this system. So if you take that nonlinear Schrodinger equation, you find what the normal modes of the system are. And if I look on small enough scales, so large enough wave numbers, I find a quadratic dispersion relationship, which looks like this. So this is very characteristic of a non-relativistic system. And in fact, this expression is exactly what you would get at all scales for just the Schrodinger equation. But then if I zoom out and I look at larger scales, so smaller wave numbers, I get a linear dispersion relationship. And this is because of that nonlinear term kicking in that gives you this kind of dispersion relationship, which is exactly what you would get for a massless relativistic field. So you can see it looks like some speed, c, times the wave number k. Now, in a relativistic theory, this speed c would be the speed of light. In our system, it's the sound speed of the phonon modes, these modes at long wavelengths, but it's completely analogous to a massless scalar field. If I just forget that this c is the sound speed and I think of it as being an analog of the speed of light. So that's all well and good, but I'm not interested in massless fields. I want my field to have some potential so that it can evolve between different vacuum states. So how do we get that? So we have to make our system slightly more complicated. So rather than having a single atomic cloud, I need to have two clouds. So concretely, these would be made up of two different hyperfine states of the same isotope. And they're in the same position and they can talk to each other if I shine a coherent electromagnetic field on them with the right frequency that one type of atom can turn into the other type of atom and vice versa. This is what we would call a Rabi coupling. And it turns out that if I do this and I look at the phase difference between those two species, those two clouds, I very naturally get this cosine potential for that relative phase. And this is very easy to understand intuitively, because if I put my two species, the two clouds, in antiphase, so a relative phase of pi, this is going to be unstable because the two species talk to each other, they want to have the same phase, and so they'll want to drop down here into the true vacuum where they're in phase with each other. And you can see that this will be periodic because I don't care whether the relative phase is 0 or 2 pi, etc. The system will look the same. So very good. I already have an interesting early universe theory. This is what we would call a Sine-Gordon model. But as you can see, there's no false vacuum here, right? If I start it at the top of this hill, it will just immediately drop down. So that means no bubble nucleation. So really what I need to do is I need to, do something fancy to my system to make this antiphase state, this pi phase difference, metastable. So create a false vacuum there. It turns out the way that you can do this is by taking that coupling between the two clouds and rapidly modulating it in time. Now, this is not immediately intuitively obvious why this works, but there's a very nice analogy to a classical pendulum. So a classical pendulum also has a cosine potential. If I start it upwards like this, it wants to drop down. But if I rapidly modulate the pivot point of this pendulum, you can make the upward position metastable. And you can kind of see that in this GIF here. So mathematically, this is completely equivalent to what we're doing here. So we make this antiphase state that was unstable, we make it metastable. And what that means is if I prepare my system in this state, which is very easy to do by manipulating the atoms, I can then just watch and wait and see how long it takes to escape the false vacuum by forming bubbles. So now if I go back to the dispersion relationship I had before, remember that on small scales, it was quadratic, which was non-relativistic. So we still have that. It's still, if I zoom in close enough on my system, I see that it's made out of atoms and it's not actually a fundamental field. But in the IR, where I had a linear dispersion relationship before, I now have this mass gap, right, associated with the curvature around the false vacuum. So in this IR regime, this looks exactly like that Klein-Gordon theory that I wrote down on the first slide. So this is wonderful. This is exactly what we wanted. In fact, I can go even further. So that's, the dispersion relationship is kind of talking about the classical dynamics of little fluctuations in this system. So a calculation that we did was also to look at the quantum fluctuations. So I can take this system with this modulated coupling and I can derive what is the power spectrum of the vacuum fluctuations in this system. And what we find is, again, on small enough scales, you see that, okay, it looks non-relativistic. I get something a bit different. But if I zoom out and just look in the IR, it looks exactly like this Klein-Gordon field. So both in terms of the classical dynamics and the quantum behavior on large scales for these small fluctuations, it looks exactly like the theory that we want to simulate. So all of that discussion was for little fluctuations. You can actually go even further and study arbitrarily large deviations in this relative phase field, which is what we want because we know that the bubbles are a non-perturbative thing with large deviations in the phase field. So I can be even more demanding and say it's not good enough for it to work for small fluctuations. I need it to work for really large departures in this field. And the analogy still works for this system. So if I crunch through and do all the calculations, what I find is in the right experimental regime, this relative phase obeys this Klein-Gordon equation, where U is this potential as shown on the previous slide, or a few slides ago, with the false vacuum and the true vacuum. Turns out that the other, phase field in the system, so the total phase rather than the relative phase, is also a nice early universe theory, except it's massless. So you have these two fields, and you have to be careful to tune the system such that these two fields decouple to each other, so they don't talk to each other. But we have managed to show that this is very generically, it's possible to do this for many different kinds of atomic system. So to conclude this kind of part of the talk, what we found is that you can create this really nice detailed quantitative analogy with a early universe false vacuum theory for a very, very broad class of atomic systems. So I'm now going to move on and tell you a bit about some of the theoretical work we're doing to understand this analogy in more detail and also to kind of prepare to maximally exploit the experimental data once we have it. And the main tool that we use for doing this is these semi-classical real-time lattice simulations. So I've already shown you a few results from these in the kind of introductory part of the talk. So just to tell you a little bit briefly about this method. So it's sort of the opposite from what is done in the Euclidean approach. So in that approach, you kind of forget about fluctuations in the initial field configuration. You just write down phi as some constant value in the false vacuum. And then your field takes a very non-classical path in imaginary time, and you end up with a bubble. And there's a very well-developed kind of machinery for calculating how this happens in imaginary time. What we do is sort of the opposite in the sense that I put all of the quantumness of the problem into the initial conditions. So I initialize my simulation by drawing a random realization of the vacuum fluctuations. So that's where I'm putting the H bar, if you like. And then I just evolve classically in real time because I don't know how to do quantum real time evolution on my classical computer. But you can show using what's called the truncated Wigner approximation that to leading order in H bar, this should be equivalent. So you should still get a semi-classical description of this quantum system. So by repeating this many, many, many times, I can look at different possible initial realizations of these quantum fluctuations, and I evolve them all classically. And what we should find is that the ensemble average over this, big set of simulations gives me the same, the quantum statistics to leading order in H bar. So this was first applied in this really nice paper by Jonathan Braden and co. And we've been using it a lot in recent years to try and understand real-time dynamics of vacuum decay. So that was a lot of words, and now I'm going to show you some simulation videos for this. On the right-hand side, I'm simulating just the pure Klein-Gordon equation. So this is what the relativistic theory would look like. And on the left-hand side, I've tried to match the initial conditions, although the match isn't quite perfect for reasons we can talk about. And this is for the full analog system. So with the coupling between these two atomic species that is modulated in time. And what you can see is that, the analogy looks pretty good, right? I form a bubble, the bubble expands in this relativistic way, rapidly reaching the speed of light. But there are clearly some differences as well between the two. And this is something which we have a few ideas for what could be causing this, and we're actively kind of trying to understand this. So if people are interested, maybe that would be a good topic for the discussion session. So these simulations allow you to extract observables that we can compare with the Euclidean approach and hopefully eventually as well compare with the experimental data. So one really obvious one is nucleation rates, right? This is very easy to extract. You just run your big ensemble of simulations. So here in this plot, I'm showing each kind of faint line is one simulation, and I've kind of picked out a couple to show the general behavior. So you start down here near the false vacuum. I should say this is the volume average of the field value. You start near the false vacuum, a bubble nucleates, you rapidly kind of start gobbling up the volume, and you eventually saturate near the true vacuum, and then kind of hover around there. And from this, you can create these curves, which are the survival probability as a function of time. And it turns out if I do this and I vary the parameters of the system, then this decay rate, the slope of these curves, changes in exactly the way that I would expect from the Euclidean theory. So this is a really non-trivial check that matches what we would expect. There is, however, an important difference, which is the overall kind of global normalization of this decay rate. It's significantly faster in the lattice simulations than it is in the Euclidean predictions. And I think, we have some ideas for what might explain that in terms of renormalization of the potential on the lattice. And again, that might be a good topic for discussion if people are interested. But before I wrap up, I just wanted to highlight something that I'm really excited about to do with this. And this is work that has been led again by Dalila Pirvu and Matt Johnson and collaborators. And this is looking beyond decay rates. What are new observables we can extract from the analog experiments and from the lattice simulations that we can't access with the traditional kind of Euclidean techniques? And there's all kinds of things that Dalila and Matt and collaborators have discovered, which I think are really, really nice. So for example, the bubble correlations that I mentioned earlier on in the talk, you can also see peculiar velocities. So when the bubbles form, they tend to be boosted with respect to the simulation frame. That's really interesting as well. But one that I'm also super excited about is these oscillon precursors. So if you take all of the bubbles that form in your ensemble and you deboost them into their rest frame and you stack them, you can get this profile of kind of the average bubble. And you can see from this time onwards, it looks very much like what you'd expect. It just starts expanding. But if I go back in time and I look before the moment of nucleation, you see this kind of coherent precursor object. And I think this real-time precursor is completely missing from the standard description of bubble nucleation in Euclidean theory. And in fact, what Dalila and co were able to do is trace these precursors backwards in time in individual simulations and see they're these kind of oscillating blobs of scalar fields that we would call oscillons. And I think this is a really beautiful and really new way of thinking about vacuum decay that is very different from the kind of previous received wisdom. I'm going to speed up a bit because I'm almost at the 30 minutes. So there's a couple of open problems that we are still thinking about how to solve. One is this renormalization I mentioned before. There's also questions about parametric resonance of the modulation of the coupling in these experiments. But again, this is something that we're not too worried about. One problem that was solved very recently is to do with the boundaries of the experiment. So this was in this paper I put out last month. Where basically because your system is sitting in the lab, it needs to have some edge to it, but clearly the universe or the multiverse doesn't have an edge. And generically, this edge is very problematic because it can cause very rapid nucleation of bubbles on the edge of the experiment, which kind of would obscure the rate at which bubbles are forming in the center, which is what we want to observe. And what we've shown is that using the incredible experimental control that these experiments have, you're able to design the edge of the experiment so that you make it completely inhospitable for bubbles. So bubbles cannot form at the edge of the experiment, and you only see them forming in the middle. So this is an example of the kinds of problems we're solving with the experiment to bring us closer and closer to an ideal simulator of the early universe. So I'm going to wrap up there. I hope I've convinced you vacuum decay is super interesting, especially if you're someone who's interested in multiverse scenarios. But we actually don't understand it very well, in particular in real time or in situations where you don't have symmetries that you can rely on. And so we are pioneering this approach of testing vacuum decay empirically in the laboratory using these analog experiments. And yeah, we're hoping to have our first science data, within hopefully the next year or so. So please stay tuned and look out for those results. Thanks very much for listening.